Hello friends, welcome to YouTube channel Electronics. In this video, we will learn depletion type of MOSFET. All electronic devices have processors inside them. These processors have special type of transistors called MOSFETs inside them. In earlier video, we have discussed BJT. We have also discussed FET types and JFET, junction field effect transistor, in detail. So in this video we will focus on MOSFET, metal oxide semiconductor field effect transistor, also called IGFET, insulated gate field effect transistor. MOSFET can be further classified as depletion type and enhancement type MOSFET. Both of these can be either N-channel or P-channel devices. The transistor family tree is shown in this block diagram. We will focus on depletion type MOSFET in this video. MOSFETs have three terminals named as gate, drain and source. Let's quickly discuss the construction of a N-channel MOSFET. Just take a block of P-type semiconductor. This block will be a base for MOSFET. We also call it as substrate. The entire MOSFET will be fabricated on this substrate. Next, two highly doped N-type semiconductors are diffused on this substrate. Source and drain terminals are brought out through metallic contacts from these two N regions. Another heavily doped N region is added between the drain and source regions. Now the entire surface of the substrate is coated with an insulating layer of silicon dioxide. On this layer of silicon dioxide, a thin metallic plate is placed and a gate terminal is brought out from this metallic plate. If we observe over here, the gate contact is insulated unlike source and drain contact. This is how an N-channel MOSFET is constructed. A P-channel MOSFET is similar in construction except that uses N-type substrate and two heavily doped P regions are diffused on it. Source and drain terminals are directly connected from them. Another heavily doped P region added between them. Here also gate contact is insulated by silicon dioxide unlike source and drain contact. This is the constructional feature of a P-channel MOSFET. In some MOSFETs, this substrate terminal is also available externally. If we see the electronic symbols of the depletion type of MOSFETs, they replicates the actual construction of the MOSFET. This line which connects the drain and the source terminals represents the channel. Further, there is a space between gate terminal and the channel. This represents the gate terminal is isolated from the channel. In some MOSFETs, substrate pin is also available. So in that case, MOSFETs are represented by these symbols. Now if you observe the N-channel and P-channel MOSFETs, then the only difference is that the direction of this arrow. So if it is going inward, then it indicates the N-channel MOSFET, and if it is going outwards, then it indicates the P-channel MOSFET. Basically, the arrow position represents the direction of flow of current. In most of the MOSFETs, substrate terminal is internally connected to the source terminal. In that case, these symbols are used. Here we can see that substrate terminal is not shown. It is shorted to the source terminal. In MOSFETs, due to the gate terminal is isolated from the channel using SiO2 layer, there will not be any current flow through this gate terminal. Or we can say that the input impedance of the gate terminal is very high, and that's why MOSFETs are used in minimum power consumption applications. Now let's see the operational features of the depletion MOSFET. If we apply a DC voltage VDS between drain and source terminals, like here, positive voltage to the drain and negative voltage to the source terminal. Now what will happen here is that the free electrons in these N channels will get repelled from the source terminal's negative voltage and gets attracted towards the drain terminal's positive voltage. So there is a flow of electrons between source terminal to the drain terminal, and in this way the current flow will establish in the depletion MOSFET. Remember, here we are speaking about movement of electrons, but the conventional current or holes flows in opposite direction. So here in depletion MOSFET, the conventional current or hole current flows between drain to source terminal. Let's say the conventional current that is flowing into the drain terminal is called ID, and the conventional current that is flowing out from the source terminal is called IS. And we can say that this ID and IS are equal. If we keep on increasing the voltage VDS between drain and source terminals, the electrons will move faster between source terminal to drain terminal because of the increase in repulsion from source terminal and increased attraction from drain terminal, which means the current flow increased in the depletion MOSFET. If we represent the current ID versus VDS in a graph, ID in x-axis and VDS in y-axis, initially it looks like a straight line because as we are increasing the voltage VDS between drain and source, the drain current ID will also increases linearly. As we further increase the voltage VDS, at one particular voltage, the drain current becomes constant or reaches to the saturation. So here in this output characteristic curve, the slope of the line changes and it becomes horizontal. This saturation current value is known as IDSS. Here we haven't applied any voltage at the gate, or we can say that the gate voltage is 0. Here we can assume that the gate and the source terminals are connected together. So voltage between gate and source VGS is equal to 0. Hence the value of the saturation current for VGS equals to 0 is known as IDSS. Now let's see what happens when we connect a negative voltage VGS between gate and source terminals. Because of the insulated SiO2 layer between the gate and the N-channel, the electrons will not be able to pass through it. So negative charge will develop at the gate terminal. If we observe over here, this portion, the gate and N-channel will behave like a capacitor because there is a dielectric material between conductor and semiconductor. Hence it behaves like a capacitor. So the negative voltage at the gate terminal will repel these electrons towards the substrate. As we know that the majority charge carriers in this P-type substrate are holes. So the electrons in the N-channel will recombine with the holes in the P-type substrate, and at the same time the holes in this P-type substrate will also get attracted towards the negative charge at the gate terminal. In short, what happened here is that positive charge developed in this channel. This will form a channel of positive charge carriers even inside N-type semiconductor. Hence there will be reduction of free electrons, and as a result the conductivity or the channel width is reduced. So the electrons which are flowing from source to drain now must have to flow through this narrow gap to constitute current. This will result the reduced current flow in the depletion MOSFET. If we increase this negative gate voltage VGS, this will further increase this positive charge inside the N-type semiconductor, and effectively it reduces the flow of current in the MOSFET. If we further increase this negative voltage at gate terminal and at one particular voltage, the N-channel will get closed by the positive charge and there will be no current flow in the depletion MOSFET. So the rate of recombination of electrons and holes in this N-channel depends upon the applied negative voltage at the gate terminal. You can see this from the graph. As the value of VGS is negative, for example -1 volt, the value of the drain current will reduce. The drain current will keep on reducing as the value of VGS keeps on decreasing, like -2 volts, -3 volts, and etc. And at one particular voltage, this drain current will become 0. So this voltage of VGS is known as the pinch-off voltage. This region of operation of a MOSFET is known as ohmic region. In this region, MOSFET behaves like like a variable resistor, and this region of operation is known as saturation region. In this region, MOSFET works as a constant current source. If you compare the depletion MOSFET and JFET's output characteristic curves, they both look quite similar. But the depletion MOSFET also works for the positive value of the VGS. So now let's see what happens when we apply a positive voltage VGS at gate terminal. As we know, the minority charge carriers in this P-type substrate are electrons. So whenever we apply the positive voltage at this gate terminal, the gate terminal becomes positively charged. And here, due to capacitive action in this region, the electrons which are minority charge carriers in this P-type substrate will get attracted towards this N-channel, and due to that the N-channel width gets increased, or we can say that the number of free electrons in this N-channel will increase. So the electrons which are flowing from source to drain have wider channel width, and there are more number of free electrons to constitute current flow. Hence effectively we can say that the flow of current in this depletion MOSFET will increases. We can draw this in output characteristic graph. For the positive value of voltage VGS, the drain current ID will be even more than this saturation current IDSS. Now let's see the transfer characteristics of depletion MOSFET. Transfer characteristics defines the relationship between input and output quantity. Here it defines the relationship between output, the drain current ID, and the input, the gate voltage VGS, for the fixed value of drain source voltage VDS. Here we will get the value of output current ID for the negative and positive values of VGS. So due to this, the curve will extended towards both sides. As we have seen that whenever this VGS is positive, then the channel width or number of free electrons in the channel will increases, and whenever VGS is negative, then the channel width or number of free electrons in the channel will decreases. Hence this region where VGS is positive is known as enhancement region, and this region where the VGS is negative is known as depletion region. The relationship between the output current ID and input voltage VGS can be expressed by the expression drain current ID equals to IDSS times 1 minus VGS divided by VP whole square. So using this expression, we can find the drain current ID for the different values of VGS. Now let's briefly discuss about the P-channel depletion MOSFET. As discussed earlier, P-channel MOSFET is similar in construction like N-channel MOSFET, except it uses N-type substrate and P-type channels. In P-channel MOSFET, free electrons are majority charge carriers in substrate, and holes are majority charge carriers in the channel. So the polarity of the applied voltage will also gets reversed. That means this voltage VDS will be negative and this voltage VGS will be positive. First of all, let's see how the current will flows whenever VGS is equals to 0. Here drain terminal is connected to negative supply. So the holes will enter from source and flows towards drain and will get attracted towards the negative terminal. Let's say the conventional current flowing into the source terminal is IS and the current flowing out from drain terminal is ID. Here we know that ID equals to IS. Whenever we apply a positive voltage VGS at gate terminal, the gate terminal will be positively charged. Here, because of the dielectric material between conductor and insulator, this region will behave like a capacitor. So the positive voltage at the gate terminal will repel these holes towards the substrate. Hence the holes in the P channel will get recombined with the electrons in the N-type substrate, and at the same time electrons in this N-type substrate will get attracted towards positively charged gate. Hence the negative charge develops in this channel. So negatively charged channel forms inside the P-type semiconductor. As a result, P-type channel width will reduces. Because of this narrow gap, there will be a reduced current flow between source to drain terminal. Here, by increasing or decreasing this gate voltage VGS, we can control the current flow in the depletion MOSFET. So, if you observe the drain curve or the output characteristics of this P-channel MOSFET, this voltage VDS is negative. As we keep on increasing the VGS voltage to positive, then the drain current ID will keeps on reducing, and at the pinch of voltage, drain current ID will become 0. And whenever this VGS is negative, then the value of drain current ID will be higher than the saturation current IDSS. If we observe the transfer characteristics, then it will look quite opposite to the N-channel MOSFET. Now let's discuss briefly some applications of depletion MOSFETs. Depletion MOSFETs are generally used where an application demands current flow at 0 gate voltage, like startup circuit of SMPS. Here in this circuit, the depletion MOSFET provides the initial current required by the PWM IC to kickstart the operation. The main advantages of this approach are DMOSFETs dissipates 0 power, so overall efficiency is improved. DMOSFETs are also used as surge protection for linear voltage regulators. Linear voltage regulators provides power to small analog circuits. The depletion MOSFETs are connected across voltage regulators in telecommunication circuit and aviation electronic circuits to mitigate transients caused by lightning strikes and inductive loads. The depletion MOSFET can be used to implement a constant current source. It provides constant current in LED drivers and trickle charger circuits to maintain battery charge for surveillance system. Depletion MOSFETs used as high voltage ramp generator. Applications such as automatic test equipment requires high voltage ramps with a linear relationship between output voltage and time. Depletion MOSFETs used in high voltage protection circuits. They are used to protect measuring instrument against destructive high voltage caused by accidental connection. The depletion MOSFETs are excellent to implement solid state relays for load switching in place of electromechanical relays. Applications such as medical equipments, consumer electronics are examples where solid state relays are widely used. That's all about depletion mode MOSFET. If you have learned from this video, please do mention them in the comment section below. Thanks for watching. If you like this video, please click the like button. Help others to learn by sharing this video. Please subscribe and turn on notifications for more such videos. Have a nice day.